Okay.
So, hello everyone. So, welcome to the first ACM seminar series. I'm very pleased to launch this new seminar series so that I hope everyone enjoys the new trend in applied and computational math. And our first speaker is Richard Park from KAIST. So, Richard. So Richard received his PhD from Texas A&M University, and then he was to do his postdoctoral training at the University of Iowa in the math department, and then he joined the KAIST in my group as a postdoc. And today we are going to talk about physics-informed neural networks, learning the homogenized coefficients of the multiscale elliptic equation. And just for your information, this talk will be recorded and loaded on our YouTube channel, ACM, so that please subscribe, then you will find the recorded talk later on. And please welcome Richard.
Okay, sorry about the delay, and thank you very much for the
You can reshare the screen from the Zoom. Oh, okay. Did you connect it through Welcome KAIST?
No.
Which one you want to find?
So
Actually, tell me the Wi-Fi information.
yes,
Therefore,
yes.
Yeah,
let's,
you can
2214.
2214.
and
Message side 2216.
Okay, so thank you very much for coming to my talk, and I would also like to say thank you very much for attending this ACM seminar. I'm one of the organizers, so I'm very glad and honored to get this first presentation for this ACM seminar today. Again, sorry about the delay, and today I'll present my recent work, physics-informed neural networks for learning the homogenized coefficient of multiscale equations. This is a joint work with Professor Shuiyu Zhu from the University of Iowa. Okay, so a wide range of scientific engineering problems involves multiple scales. So if you look at these two pictures, they represent heterogeneous porous media and the fiber materials. So due to their complex geometry, if you focus on this small region represented by these red squares, we can still see that we have some fine scale variation even inside this small region. So typically the media like this have their own macroscopic structure. Okay, but if we focus on the small region, then we can still see some fine scale oscillations as well. So we say that this type of media have the multiple scale in that sense. Okay, so due to their complex geometry, their properties like permeability. So if you in real life application, if you want to do some flow simulation on this porous media, then we need this permeability coefficient, but our permeability coefficient in this type of media should have some very fine scale oscillations or variations. Okay, so the direct numerical simulation is very expensive because we need to completely resolve the fine scale feature in our media of interest. Okay, so some type of model reduction is needed. So we need to average or capture our micro scale effect and bring them onto the macro scales. So that motivates the homogenization and the drill limit. So here we have our example. We have this 1D multiscale elliptic equation. So I call this a multiscale elliptic equation because of this epsilon feature here. So the epsilon is typically a very small positive number, and that represents micro scale oscillation size. And if you look at this coefficient, we call this multiscale coefficient A epsilon. You can see that we have this slow variable x that represents our macroscopic behavior, and this variable x over epsilon that represents the fine scale oscillation here. Because this is a sine function, if you look at the sine function part, you can easily see that the period is epsilon here. So this epsilon, because this epsilon is a very small number, we can see that our function here should have very fine oscillations. Right? So again, the problem is challenging because of the fine oscillations, because we need a very fine mesh if you want to use, for example, FEM to solve this problem. So that motivates homogenization. Okay, so there's a lot of theory about the homogenization, but here I just want to deliver some general idea of it. So for the homogenization, we study the homogenized limit as epsilon tends to 0. So we study the limit of this equation, okay, as epsilon tends to 0. And then this is the homogenized equation, which is the limit of the equation 1, our original multiscale problem 1, as epsilon tends to 0. So this is a homogenized equation, and I first want to emphasize that this homogenized equation does not depend on epsilon any longer. So it does not have fine scale oscillation in it, and its coefficient A star is very smooth. So solving this problem 2 is much easier than solving this problem 1. But this problem 2 is the limit of this problem 1. In what sense? In a sense that if we solve this problem, then we get this solution U0. And this U0 is very close to this U epsilon here for sufficiently small epsilons. So in this sense, we say that this problem 2 is the limit of this problem 1. So this smooth coefficient here in this homogenized equation is called the drill limit and homogenized coefficient. And this U0, okay, the solution of 2 is called the homogenized solution. So from for the later slide, we'll always call this multiscale coefficient and multiscale solution, okay, A epsilon and A U epsilon. And U star is our drill limit or homogenized coefficient, and U0 is going to be our homogenized solution. So the goal of the homogenization is to find the drill limit here in this homogenized equation. So from now, I just want to give some simple illustration of multiscale and homogenized function and G convergence. So to give some intuition, I would like to have these two pictures. If you look at this left picture first, then you can see that this red line represents our multiscale coefficient, A epsilon. It's quite oscillatory. But if you look at this blue line, which is the G limit of it, you can see that it's quite smooth. It doesn't have fine scale oscillation. And let's look at their corresponding solutions. The red line represents the multiscale solution here, and the blue line represents the homogenized solution here. So we first can see that our homogenized solution is quite smooth. It has smooth structure. But if you look at the red line carefully, which is our multiscale solution, you can see some fine scale oscillation around the homogenized solution. Okay, so the message I want to deliver here is the homogenized solution U0 is nearly the macroscopic behavior of this oscillating multiscale solution. So this is the intuition I'm going to use later on. And this is a simple illustration of the G convergence. Okay, so as epsilon tends to 0, the equation 1 converges to the equation 2, the homogenized equation, okay, that I showed before. So let us see what happens as epsilon tends to 0 to our multiscale coefficient and multiscale solution here. So let's focus on the top figures. So from left to right, the value of epsilon becomes smaller and smaller. And you can see that if you look at the red lines, which represent our multiscale coefficient, you can see that the oscillation becomes rapider and rapider. And if you see this figure for epsilon equals 0.01, we see this heavy oscillation. The oscillation is quite heavy here in our multiscale coefficient. However, if you look at the corresponding G limit, if you look at their G limit, the blue line, they're quite smooth here. So think about it. So what if we solve this problem with this red coefficients here? So because the oscillation here is quite heavy, so the computation will be very, very expensive, if not impossible. Because if we use the FEM to solve this problem, our FEM mesh should be smaller than the period of its oscillations, so which means that it will be very, very challenging. But if you solve the problem with this coefficient, G limit, then it becomes a much easier task, right? Because it doesn't have any oscillation feature. Okay, let us move on to the corresponding solutions. Okay, if we look at the corresponding solution, again, from left to right, the value of epsilon is becoming smaller and smaller. And I first want to point out that the red lines, our multiscale solutions, are converging to the blue line, our homogenized solution. That's one important point. And I also want you to see these oscillation types here. So when epsilon is relatively large, you have this slow variation, okay, so slow variation of the coefficient of the solution, sorry. But as epsilon tends to 0, the oscillation becomes rapider and rapider, but the amplitude is becoming smaller and smaller. So if you look at this picture with epsilon equals 0.01, we can see that the red line and blue line almost coincide, so which means that our red line multiscale solution is close, very, very close to our homogenized solution enough. That means, so instead of solving this problem with this red multiscale coefficient with heavy oscillation, if we can find this G limit, okay, if we can find this blue line G limit, then we can solve this problem with this smooth G limit, and which is much easier and cheaper. Then, yeah.
You mentioned that when epsilon is close to 0.1, because of the oscillatory behavior, it's very challenging to solve without FEM. And my question is then how you compute the reference solution below?
Oh, I used very, very fine mesh. Yeah, it took some time, but it's a one-dimensional problem. So yeah, to generate this figure, it was not too bad. But yeah, but yeah, I still, for the reference, I spent some time here to generate all the results.
Thank you.
Okay, so if we can find this tree limit, what we solve this problem with this coefficient tree limit, and what we get for the solution is this homogenized solution, blue one. And because this blue solution is very close to the red solution here, you cannot even distinguish those two in this figure. So the red line here represents the solution corresponding to this heavily oscillatory multiscale coefficient. So which means that if we solve this problem with the tree limit, then we can get very good approximation to the multiscale solution that correspond to this heavily oscillatory coefficient. So it's really important task to find this tree limit, okay? But unfortunately, it's not very straightforward or trivial to find it. So as you can see, here, the tree limit, the blue line, is not some type of strong limit of the multiscale coefficient, right? When epsilon is very small, the multiscale coefficient should still have this oscillation, but the tree limit is quite smooth. And unfortunately, again, it's not some type of average or weak limit of the multiscale coefficients as well. So it requires some technique to find the tree limit. So that's the homogenization. So this is the traditional homogenization procedure. So for the traditional homogenization, we assume that our multiscale coefficient A epsilon is periodic with respect to this fast variable y, x over epsilon. And let's say this y is the period. Okay. Then to find the tree limit, we first need to derive and solve the local problems in this period y for each fixed x in our domain with the periodic boundary conditions here. So which means that we have to derive and solve the last observed set of problems to compute the tree limit, which is computationally very expensive. And after solving all of these problems, we can finally get this tree limit from the solution of the equation 3, which is called the Sept problem. So it's computationally expensive. And in addition to that, there's another challenge because it's not quite clear. So in some specific case, it's still possible to handle non-periodicity, but in general, it's not clear how to get our tree limit from a non-periodic multiscale coefficient. Right? So if some data are available, there have been a lot of attempts to actually recover the homogenized or reduced system from high fidelity or multiscale data. But I'm not going over all of these methods, but the point is these methods are quite robust, but they require some periodicity of the multiscale coefficient or some explicit form of the multiscale coefficient. So here's our problem setting. So motivated by the previous development, we want to consider this problem. So we consider elliptic multiscale equations here, but we don't want to rely on any periodicity or no known form for this multiscale coefficient. Okay. So we want to try this inverse problem of learning the tree limit, okay, and homogenized solution associated with this original multiscale equation with some data. Okay, so I'm going to talk about what type of data we use in one of the later slides. Okay, so here our wish list is to recover the tree limit without relying on any periodicity or explicit formula of the multiscale coefficient A epsilon. Okay. So based on the theory of homogenization of the elliptic equations, we know the form of the homogenized equation. But only thing we don't know is this guy, the G limit in it. Okay, so we want to recover this G limit using some data, so using some inverse problem. The natural way to think of this inverse problem of recovering the G limit is to use the corresponding solution data, right? Which is the homogenized solution data. Okay, so that's the natural choice. The natural choice is using homogenized solution data. But we need to think about what type of data are available in practice. Okay, so because the problem is the homogenized solution data are typically not available in practice. So in real life application, when we collect some data in our multiscale media, then the data we collect are affected by the multiscale feature. So for the general setting, we want to use this multiscale solution data as a surrogate of the homogenized solution data. But can it be a good surrogate? The answer is yes. The answer is yes, at least when epsilon is very small. So if you look at, if you recall this picture that I showed in one of the previous slides, then this blue line is our homogenized solution, and the red line is our multiscale solution. So they virtually look very similar. So this blue line is almost the macroscopic behavior of the multiscale solution. But we have some problem here, of course, because our multiscale solution have this oscillatory feature. So there's some data mismatch between the homogenized solution and the multiscale solution. Okay, so ideally we have to use homogenized solution data, but actually we use the multiscale solution data, but the problem is there are some mismatch because of those oscillations in our multiscale solution data. So can we handle that? So we need some type of good regularization method to handle that. All right, so we choose to use this physics-informed neural network for the regularization of our inverse problem. So PINS has been utilized for both forward and inverse problems involving PDEs successfully. And the basic idea is to approximate the solution and the coefficient by the neural network. And this is the key part. We incorporate our homogenized equation into the loss function. Okay, so that's our strategy. So this is some schematic description of our physics-informed neural network. So we first need to construct these two separate neural networks that are going to represent our solution approximation and the G-limit approximation here. And we modify our solution network so that our solution network will automatically satisfy the exact boundary condition. So I'm not going into detail about this today. And the key part is this loss function, the physics-informed loss function. In this loss function, we first have this term taking into account our data fit. And additionally, we also have this term taking into account the PDE residual. And this, because we embed our PDE, the method is called physics-informed neural network or physics-informed loss function for this specific loss function. Okay, we call it that way. And so as you can see, ideally, if we have some good approximation, this should be ideally 0. Okay, and this also, because this represents our data fit, this should be also ideally near 0. Okay, so we want to minimize this loss term. Okay, to find some optimal network parameters, which give us the approximation of the G limit and the homogenized solution simultaneously. Okay. So if we take a look at our loss function, then we have these two terms. This lambda r and lambda d are the weights that can take into account the balance between these two loss terms. Okay, and the first loss term consider our PDE residual, and the second loss term here consider our data fit, and these are evaluated at some training points TR and TD respectively, and those two training points are chosen from our domain, okay, our spatial domain. Okay, so we evaluate our loss functions in our training data at our training data, and from now I want to give some numerical implementation results of our method. Okay, so we consider like two different scenarios. Okay, so in the first scenario, we know the multiscale coefficient A epsilon. So in this case, we have this forward solver, okay, to generate noise-free multiscale solution data. And in the second scenario, where we don't know the multiscale coefficient, we can only generate some noisy, okay, multiscale solution data by some sensors. Okay, so we'll consider these two practical scenarios. Okay, and for the noise-free data, we generate the data by solving our original multiscale equation via FEM solver with fixed fine mesh. Okay, and then to generate the noise data, we add 1, 3, and 5% standard normal noise to the noise-free data we generated. Okay, and from now, these two A hat and U hat are going to represent our pin's approximation to the G limit and the homogenized solution. Okay, and these two will represent our reference G limit and homogenized solution respectively. Okay, so they can be exact ones or they can be computed by some existing method like FEM. Right. So,
Typically,
yeah.
you mentioned earlier that when epsilon is small, it's quite difficult to generate what's the corresponding solution.
Mm-hmm.
And when you generate the training data, then it seems to me that epsilon cannot be too small because of that difficulty.
Oh, okay. Yes.
So are you assuming that epsilon is sufficiently large enough so that you can easily generate the data?
So training data, for training data, we only need to choose some points from our domain, right? So and for those training data, what I want to learn is the homogenized solution and homogenized and the G limit, which are quite smooth. So
right, but to generate the training data, say epsilon 10 to the minus 3.
Yes.
And to generate the corresponding solution,
Uh-huh.
it's called FEM.
Uh-huh.
But you mentioned earlier that when epsilon is small,
Mhm.
you need to generate a lot of mesh. So
Yes,
it's
right.
challenging.
Yes.
So what I'm asking
That's right.
is, are you using the data
Uh-huh.
when epsilon is not that small so that you
Uh-huh.
can efficiently generate the data?
So actually, so as I said, I spent a lot of time to generate this the solution data using FEM. So I use some HPC to generate the data. So I still handled very small epsilons, like up to I think 2 to the negative 10 or something. Then yeah, in that case, I really needed to have a lot of the finite elements there. So yeah, it took me quite a long time to generate all the data or the reference solutions. Yeah, but or sometimes fortunately I had some like analytical solution. So yeah, in those cases I didn't need to generate any. Yeah.
Thank you.
Mm-hmm. Okay, so to check the validity of our method, we first try this example. But for this example, you can see that we have this locally periodic coefficient because it depends on this macroscopic variable x and the phase variable x over epsilon. And you can see that it's periodic with respect to our phase variable. So we call it a locally periodic multiscale coefficient. But in this case, the traditional homogenization has been well developed, so we know the analytic solution, so analytic limit. Okay, but we still want to check the validity of our methods. That's why we tried this example. Okay, so I first want to present the result with different fine scale parameters epsilon. So we have these two fine scale parameters, 2 to the negative 3 and 2 to the negative 7. And the red line represents the ground truth G limit. In this case, it's exact G limit. And the blue line represents our approximation. So when epsilon is relatively large, we do expect our approximation to G limit is not 100% accurate, and not very accurate here, but you can see that it can still capture some major behavior of the G limit. And we have quite accurate result for the G limit when epsilon is quite small. So if you look at the bottom figures, they represent the solutions. So here the black dots represent our multiscale data. So data we feed to our neural network. Okay, and the red line represents the ground truth homogenized solution, and the blue line represents our approximation. So here what's interesting is when epsilon is quite small, like 2 to the negative 7, we do expect pins can do a good job. Because if you look at our data itself is already very close to our ground truth homogenized solution, the red line, right? But if you look at this case where we have relatively large epsilon, you can see that there's some deviation between our multiscale data and the ground truth homogenized solution. But if you look at our approximation, the blue line, you can see that it's following the behavior of the ground truth homogenized solution, right? Instead of following this behavior of our oscillatory data. Okay. So this is because of the physics-informed regularization that pins provide. And this is the result for a fixed epsilon with some different noise level. Okay. If we have the high noise corruption, then you can see that our result for the G limit becomes a little bit worse, but not too worse. It still captures the major behavior of the G limit. Okay, even with the 3% noise data. And if you look at the corresponding solution figures, when we have noise-free data, we of course have some good results. It was expected, but with this noise corruption, even though we can see some noticeable noise corruption in our data here, you can see that our approximation blue line approximate, okay, this red line, our homogenized solution pretty well. So even though we have our oscillations in our data, because of the physics-informed regularization, we can recover the smooth, okay, the smooth homogenized solution pretty well. Okay, so we can see that in this example, the pins can filter out some noise or multiscale features very well. Okay, so I want to also present the error result for with respect to the fine scale parameter epsilon. So the left figure represents the error relative L2 error result for the G limit, and the right one represents those for homogenized solutions. Okay, and these 4 lines represent the result from noise-free and 1% noise-free data, 1%, 3%, and 5% noise data. So if you focus on the noise-free case, okay, we can see some convergence. This was expected because as epsilon tends to 0, our data, the multiscale solution, converges to the homogenized solution, our ideal data, right? Okay. But with some noise corruption, okay, with some noise corruption, we can see that this convergence tendency has been mitigated. This is because our noise is dominant over our fine scale features, so over epsilon. So the convergence becomes mitigated, okay, here. But nevertheless, we could still achieve some errors less than 10 to the minus 1. So roughly all the errors for from the 5% noise result are around like are scaled as 10 to the negative 2. So the result was not too bad, even with the high noise corruption. All right. So this is our second example. So here in this example, if we look at our multiscale coefficient and the corresponding figures for epsilon equals 2 to the negative 3 and 2 to the negative 5, then we can see some heavy oscillations in our multiscale coefficients. Okay, so even though this problem is kind of periodic, this is non-standard problem because of this behavior, this special type of oscillation. So it requires some techniques other than the traditional homogenized method. Okay, so so we want to see how our method, our algorithm pins perform with this problem. So this is the result of noise-free data with different epsilon. So with small epsilons, we can successfully recover the limits pretty well. And if you look at the corresponding solution data, you can also see that for small epsilons, our approximation to the homogenized solutions are very accurate here. Okay. Right. So these are the results with different noise level. So with high level of the noise, we do expect that we will have some not very accurate results. But when we have noise-free data or 1% noise data, we can successfully capture the major behavior of the drill limit with the pins. And also here, we can observe the same thing as before. So even though we have some noise oscillation, noisy feature in our multiscale data, our approximation only take into account the macroscopic smooth behavior of it, which is very close to the ground truth homogenized solution. So that's how the pins provide the physics for neural network in order for us to have some good approximation to the smooth, okay, homogenized solution, even though we have some like noisy or multiscale oscillation in our data. So these are the errors with respect to epsilon. Here you can see some more clear convergence if you compare this with the previous example here. But still, we can observe the similar pattern here. So with the noise-free data, we have some clear convergence, but these convergence tendency are mitigated with when we have some noise corruption. So if you look at the result with 5% noise, you can see that the error stays the same, almost the same. So the error saturates from the beginning, right? So this is again because the noise effect is dominant over the effect of our fine scale parameter epsilon. Okay, so for now we consistently see that we have this type of convergence with noise-free data, right? Again, this is because our multiscale solution data converges to our homogenized solution, okay, as epsilon tends to 0. Okay, So that's why we have some advantage with the small epsilons, but even for the relatively large epsilon, you can see that we can achieve some reasonably good results in terms of this L2 relative L2 errors, okay, for both G limit and the homogenized solution. Okay, so here I would like to show another example. Here we have 2D and non-periodic homogenization. Okay, so we have this type of elliptic multiscale equation. And if you look at our multiscale coefficients here, it's not periodic in terms of x2, right? So this is a non-periodic case. So this example can be handled by so-called lambda scale convergence method via FEM, but it's not one of the traditional homogenization methods. Okay, so the challenges arise here because of the non-periodic coefficient we have. So it will be interesting to see how our method perform with this example. Okay, so these are the results with different noise levels. Okay, we have noise free and 1% and 3% noise. So even though we have like two-dimensional function, here we just plot just one-dimensional cross section of it. Okay, for at this fixed x1. Okay, and in our 2D domain, we used 1600 residual points. So and the 1600 multiscale data. Okay, so so we have some reasonably good result for the for both noise-free and noisy cases for the G limit. And again, if you look at the result for the homogenized solution, you can still see that even though we have this noisy oscillation in our data, our approximations are quite smooth. And because it is smooth in such a way that it takes into account the macroscopic behavior of our data, which is supposed to be very close to our homogenized solution. So it approximates the homogenized solution pretty well. So that's because of the physics-informed neural network that provides the physics-informed regularization. So here's some error results with respect to different fine scale parameter epsilon. Again, we can see that with noise-free data, we can see some clear convergence, okay, as epsilon tends to 0. This is again because our data, our multiscale data, is closer and closer to our homogenized solution, our ground truth homogenized solution, as epsilon tends to 0. Okay, so this is expected. But again, for the some noise corruptions, okay, we can see some error saturation, yeah, after reaching certain stage, right? It's again because we have this dominant noisy feature compared to the effect of the fine scale parameter epsilon. Okay, so that means our noisy, roughly speaking, our noisy is larger. Okay, our noise is larger than our fine scale oscillation. So okay, so traditional homogenization often requires this explicit formula or periodicity of multiscale coefficient. So traditional homogenization cannot handle some cases where we have non-periodic or non-standard coefficient. That's the current limitation of traditional homogenization method. So we developed this method. We utilize this method using pins, and our numerical evidence suggests that our algorithm can handle these homogenization problems with non-periodic problems given or some non-standard problems given some noisy multiscale data. Okay. So this is because of the convergence of multiscale solution to the homogenized solution and the physics-informed regularization that pins provide. Okay. So this is our future direction. So we want to test more complex problems or settings. For example, more complex boundary condition or more complex domain, or we're going to have some higher dimensional problems and so forth. And so far, we don't have a rigid, rigorous theoretical insight of our method. Okay, so we want to investigate more about some rigorous analysis on our framework. And you can find the reference using this website. This is a reference paper written by me and the Professor Shui Zhu from the University of Iowa this year. Okay, and so this is the end of my presentation. So thank you very much for attending my presentation again. Okay, thank you.
Thank you, Richard, for a wonderful talk. Are there any questions from the audience?
Maybe in some cases, maybe the G limit could be slightly more oscillatory.
I'm sorry?
The G limit could be more oscillatory.
The G limit could be more oscillatory. Yeah, that can be possible.
That case, maybe learn like a oscillatory G limit.
Oh, yeah. So, okay, that's a good question because, for example, if we have some source term with some oscillation, then we're going to have, so even our macroscopic behavior of the solution will have some oscillations, but it's not going to be too bad because as epsilon tends to 0, the oscillation will be just fixed and the oscillation will not be very rapid or something. Then we can always modify our structure, architecture of our network to handle that situation. So that we can also capture this macroscopic oscillation in our solution or G limit.
That's very strange question. Homogenization. So you mean we want to look at the some coefficient in the large scale. Even though there could be oscillatory, but the scale is different. So the high oscillation cannot happen. That's our intention. So just to say, okay, the limit could be more oscillatory, that's not possible.
So the question thing is it's going to be 1/8 as opposed to I feel like 1/8 isn't that.
Yeah, but that is multiscale coefficient, not the G limit, right? So the G limit is just a limit. So we have unique G limit for the same problem. With epsilon.
So back to the
Yeah.
your first slide when you showed epsilon.
So G limit means actually we want to remove the effect of all the oscillatory effects.
Right. So in this figure, yeah, the blue line is the G limit. Okay, and you can see that even though for large epsilon, I assume that this is what you meant, right? So when epsilon is kind of large, you have some slow variation, but this one, red one, is the multiscale coefficient here.
Yes, okay, so you see that picture as epsilon goes to 0, and it gives more oscillatory, but G limit shows that the blue line. So G limit cannot be oscillatory.
That's a good question.
Yeah.
Yes.
Thank you for a nice talk, and I have a couple of questions. The first one is that, as I understood in your presentation, all the examples, the coefficient AX is highly oscillatory, but not of high contrast in the sense that the minimum of AX, the ratio of minimum and maximum of AX is not very big. So I wonder if your method is applicable to the case of high contrast problems, such as AX is 1 at some point and 100,000 at some other point.
Yeah, for example, if we talk about some channelized media, then inside the channel, yeah, it's like 1,000 or even 10,000, but in the background, it's a 1 or 2. Yeah, so in that case, the homogenization itself might not be very applicable, because we have to have this like epsilon feature. Our coefficient should be represented by some fine scale parameter epsilon, but in that case, we even have some discontinuity, and that cannot be easily homogenized, because if you look at this small region, inside the small region, we're going to have multiple channels, and that causes some discontinuity and some multiple more important modes in this small area. So because there are some important multiple modes, it cannot be easily homogenized. But in that setting, what I can do is I look at the channel and the background separately. And if we have some like fine scale variation inside the channel and the background, then we can perform the homogenization separately, like inside the channel and outside the channel that way. Yeah.
Thank you for your answer. I have another question that, because I'm not familiar with the notion of G convergence. So as you said, as I understood, the G convergence means that the solution of epsilon problem converges to the homogenized problem.
Yes.
I wonder if so is there any relation between G convergence and gamma convergence for optimization problems? In the field of optimization problems, there is a notion of gamma convergence, which is a minimal requirement to ensure that a class of minimization problem converges to certain problem, in the sense that the minimizer of the class converges to the minimizer. And I think in your model problem, because your model problem is elliptic, it can be requested into some kind of quadratic optimization problem. So I think there must be some relation between this G convergence and gamma convergence.
Oh, I see. So I believe, yeah, there must be. So I'm not very familiar with this gamma convergence in the optimization field, but yeah, so it would be very interesting to see if there will be some connection. So for now, I'm sorry that I cannot give the clear answer to this question, but yeah, it sounds like there should be a good connection between those two.
Thank you for answer.
As far as I know, the convergence of epsilon to a star is sort of like the gamma convergence style. So that this convergence is not really form convergence, it's actually there exists a subsequence that converges to that, so that is via the gamma convergence concept. I think this is somehow another way of saying the gamma convergence of in the multiscale linear. Yes.
Thanks for your talk, and I'm interested in your method. So in your method, you need to make a multiscale solution for your homogenized solution. But then if you use the FEM to solve the multiscale solution, then if there are errors, the discretization error, then the homogenized solution derived from the PIN, then the solution have same discretization error, and then if you use your networks, then there are another optimization error in your solution. Then the error goes to big if you don't use very small mesh. Then you need to make an accurate multiscale solution, but then the homogenized solution cannot be useful. So you already have exact multiscale solution.
Yes. So that's a good question. So so actually for this project, we kind of mainly focus on the scenario 2, where we don't know the multiscale coefficient, and where we have to collect our data of the data measurement. We have to do some data measurement with sensor. Okay, so we focus on that part more. And when we know the multiscale coefficient, yes, right. So there are some errors, like error caused by my discretization and error between my multiscale solution data and the homogenized solution. So yeah, that will be that's a good question. So because to accurately generate my data in the scenario 1, because I need to have this a lot of mesh for the finite element method, so it's very expensive. So unless I spend a very long time, then the accuracy of my data cannot be ideally very good. So that's one problem that I have to think about. Yeah, but I would say for one-dimensional problem, it wasn't too bad. I could always get very good approximation. And for two-dimensional problem, it wasn't too bad. But if I have some higher dimensions, then the problems will arise. So I have to deal with that. So yeah, that's a good question.
For the interest of time, let's thank the return and continue the discussion during the lunch. Thank you very much.
Thanks very much.
우리 점심을 먹으러 갈 건데 원하시는 분들은 같이 오셔서 점심 드시면 좋을 것 같습니다. 점심은
아니